Have you ever paused to reflect on how such a complex, multifunctioning world we live in can provide us with endless wonders? From the revolution of polymers everywhere you see, to the ever-increasing efficiency rates of the agricultural industry. How would you react if I told you that there is this one substance who governs any industry? Let me introduce you to sulfuric acid. For the sake of showing you the importance of sulfuric acid, please take a look at the following graph. We can infer that when the market crashed in 2008, so did the price of sulfuric acid. This was no coincidence, because the demand of sulfuric acid decreased exponentially worldwide. Thus, we can infer that sulfuric acid is an excellent indicator of the industrial potential of a nation. But now, we will let Laura to explain the industrial processes to synthesize sulfuric acid.
Now we're going to briefly see the two manufacture techniques of sulfuric acid. The first one is called the lead chamber process, and the first step takes place in the Glover Tower that we can see in the left side of the picture. It is in the hot sulfur is introduced in the bottom, while the nitrous vitriol is introduced in the top, and a reaction occurs resulting in what is called the Glover acid. Then, after that, a mixture of gases that is left there goes to the lead chambers that we can see in the middle of the picture, and there it is combined and results in other reactions. The last step is to extract the sulfuric acid that accumulates in the bottom of the chambers, and that will be the definitive acid. However, there are residual gases that stay inside of the chambers, and they are placed in the Gay-Lussac tower. And that is where they are mixed with the sulfuric acid from the Glover, and the nitrous vitriol is formed. The other process is called contact process, and it is based in the use of a catalyst to convert sulfur dioxide into sulfur trioxide. So the first step of this process is producing the sulfur dioxide with two possible reactions. After that, it has to be purified, and it enters the reactor to obtain the sulfur trioxide, which is an exothermic and reversible reaction that uses a solid catalyst. So in the catalyst is where we need to have a specific temperature and pressure, and to conclude the process, the sulfur trioxide is converted into sulfuric acid. So first it is dissolved in concentrated sulfuric acid, and it produces disulfuric acid, and then that reacts with water to produce the final concentrated sulfuric acid with a concentration between 97 and 99%. That's why this second process is more used right now, because the amount of concentration is higher.
Here we have the three reactions for the obtention of the sulfuric acid. As we can see, the respective enthalpies are all negative, which means that the reactions are exothermic, that is, release energy. I'm going to focus on the second reaction because it's the most important one. We know that the equilibrium temperature for this reaction is 1056 Kelvin, so with the enthalpies and entropies we can calculate the Gibbs free energy. After the computations, we obtain that the reaction is spontaneous under that temperature and non-spontaneous above that temperature. The third reaction doesn't occur directly because it's heavily exothermic, and during this process, some vapors are originated. Now, I'm going to talk about some thermochemistry properties of the aqueous sulfuric acid that I have read in an interesting research. Firstly, the modeling of the sulfuric acid is complicated by its incomplete dissociation. There, the K2 refers to the second dissociation constant of the sulfuric acid. In this research, they compare several mathematical models to the Pitzer model. That model introduces an equation for the excess of the free energy of aqueous solutions based on virial coefficients. After comparing all those complicated models, they select the one which explains the thermodynamic behavior in the easiest way with only 4 Pitzer parameters. Finally, some conclusions can be obtained. Different K2 equations can describe the thermodynamic behavior of aqueous sulfuric acid with good to excellent extrapolation capabilities, and the thermodynamic properties of the second dissociation reactions are linearly correlated if the assessment is made using only the Gibbs energy.
Now let's move to kinetics. The study of kinetics at a molecular level also plays a preponderant role in the microscopic outcome of sulfuric acid interactions. Specifically, the synthesis of sulfuric acid is accomplished by means of these three processes. Sulfur is obtained in its elemental form. First, it is converted to liquid by melting it. Sulfur in solid state yields to sulfur in liquid state. Afterwards, it is combusted with oxygen. Sulfur dioxide is converted into sulfur trioxide. Since this reaction is in equilibrium while the product is being formed, the reverse reaction can also occur, and it can break down in its reactants. Sulfur dioxide plus oxygen in gaseous state yields to sulfur trioxide in presence of vanadium oxide. Sulfur trioxide is converted to a very concentrated form of sulfuric acid. First, it is mixed with sulfuric acid made before to obtain oleum. Then, this oleum is reacted with water to give sulfur.
In regards to the chemical kinetics involved in the synthesis of sulfuric acid, we can notice the use of a catalyst to make the second reaction of the process more efficient. The reaction takes place optimally at 450 Celsius degrees, so it will be favored at high temperatures. You need the gases to reach equilibrium in a very short time, therefore the catalyst is used. The presence of a catalyst, in this case vanadium oxide, affects the reaction by speeding it up and, in this case, forcing the equilibrium to go to the right and form sulfur trioxide. In addition, the reaction occurs at a very high rate, so heat will be released as a consequence of this. Now there are two options, there are two alternatives. One of the alternatives is to add water to the sulfur trioxide. This is added carefully as a mist, and this will create a sulfuric acid mist, which is later condensed to get sulfuric acid in liquid form. And the other alternative is to add sulfuric acid to the sulfur trioxide to form oleum, which is then diluted in water to create a concentrated sulfur trioxide in liquid form.
Thank you, Didion. Now, let us move on to the final part, applications. In this section, it will become crystal clear why sulfuric acid is regarded as a universal chemical. In fact, it is because of its various functions as a raw material and processing agent. For instance, when it comes to chemical production, sulfuric acid plays a preponderant role in the synthesis of chemical compounds, such as hydrochloric acid, nitric acid, phosphoric acid, and a variety of others. In the second place, the contribution of sulfuric acid to the refining of oil is absolutely crucial, since it is used as a catalyst in the refining of crude oil. It accounts for the majority of petroleum-based polymers, such as polyethylene, nylon, and others. This process is carried out in an SAAU unit, which stands for sulfuric acid alkylation unit, as you can see in the drawing. Yet another dimension in the applications of sulfuric acid is the processing of metal. In this case, pickling is a word used to describe the process of removing impurities, rust, or scale off the surface of metals, such as in the production of steel. However, the usage of sulfuric acid for this purpose has declined slightly in recent years as the industry has shifted to hydrochloric acid, since, in spite of being more expensive than sulfuric acid, it gives faster results and reduces base metal loss during the pickling process. To conclude, we would like to address two applications which are totally worth mentioning. In the first place, wastewater treatment must be carried out conscientiously in order to protect the people and animals living in our environment. Here is where sulfuric acid comes into play. Solid particles with chemicals such as ferric chloride, polymers, and alums will be eliminated from the water. Additionally, the wastewater will be brought back to a neutral pH level, which is a process known as new neutralization. However, as you can see in the picture, there is a common drawback to this process, which is the fact that some structures are sensitive to the impact of sulfuric acid. Finally, lead-acid batteries are the backbone of the automobile sector. In fact, they were invented by a Frenchman, Gaston Plants, in 1859, whose design is still employed in vehicles. Sulfuric acid is used as an electrolyte in a dilute form to allow the electrons to flow between the plates in the battery, which of course follow Faraday's law for electrolysis. Thank you very much for your attention, and we wholeheartedly hope that you have gained a valuable insight into the importance of sulfuric acid in our society.